Anyway, I think you can start your lecture now.
Yes.
Thank you.
A warm greetings to everyone, and let's start our presentation. Actually, it is already the 14th lecture, and this will be about the connectionist and neural reasoning mechanisms. The first block is focused on the cognitive basis of connectionist reasoning mechanism. This is the source of everything, as the Latin said, ad fontem omnia. The human brain, what we try to capture and model in different forms. Obviously, within the human brains, there are huge number of neurons, and they are partially interconnected, and there are activations which are actually producing cognitive processes in the brain. The brain can be decomposed to a interlinked structure of neurons, and every neuron has a body, has a nucleus, has inhibitors, has connector elements to others, and has dendrites and other elements to connect to other ones. So the dendrites, for instance, terminals for reception, and the axons are terminal for transmission. So this is the biological reality, what has been modeled in computation. And obviously, there are very low-level processes there. For instance, the excitation between the different elements of the neurons, where the dendrites are conveying information towards the axons, and the axons are transferring this to the other cells, and this way the synapses are actually communicating between the cells and creates a particular biophysiological state for the brain. So these are the fundamental concepts what we have to consider, and then let's look into the nature of the brain activity. The anatomical and functional complexity of the brain poses a great challenge for modeling and also for engineering. Brain activities can be recorded from single neurons, single unit spikes, or action potentials, or from groups of neurons, multi-unit recordings, or local field potentials. An inactive neuron has a resting potential of minus 70 millivolts. This is called the cell membrane voltage in a particular region. However, an active neuron exhibits a action potential of 80 to 100 millivolts, lasting a few milliseconds, that propagates down a neuron. This measurable electrochemical gradient results from the cell's selective permeability to specific ion species. This is mediated by voltage-sensitive ion channels in the membrane and produces an electrochemical gradient. The brain composition obviously means that there are certain active elements and there are interfaces between them. The interfaces are actually needed to record and modulate the brain activity with a precision and over a short and longer time scales. The human brain, which has a volume of actually 1,250 cubic centimeters in general, has 1 billion. That means 10 raised 11 electrically active neurons. And the cell body is approximately 20 nanometer in diameter. They are interconnected to one another via chemically active synapses. 20, 40 nanometer wide gaps are in between. Each neuron processes about 10 on 1,000 synapses, and therefore 100 trillion 10 on 14 such connection exists in the brain. These numbers are important for us because actually with the current computing technology, we cannot model these quantities and cannot represent their relationships in reasonable time. The chemical synapses communicate via 100 neurotransmitters with events occurring at a rate of 0.1 to 200 Hertz. This is the so-called firing rate. 50% of the neurons are electrically inactive support cells. So we can say that this sort of 10 or 14 can be reduced actually to 10 to 7, which are working. Currently, the largest artificial neural network built on supercomputers have the size of a frog brain, which is about approximately 16 million neurons. So this is how our computer-based modeling capabilities relate to the natural formation of the human brain. It's also important for us to be aware of the levels of brain function. Actually, the brain is performing on multiple levels: the behavior level, the distribution level, the specific regions level, the nerve cell level, neural compartment level, microcircuits level, organelles level, molecules levels, and the genes level. So this is how we are actually going down to the DNA and protein sequences from the observable behavior, observable performance, which can be quantified, which can be monitored, and can be reported in different applications. So it's a rather complete level structure, and very different activities are to be identified, as you can see in this overview. Let's define what connectionism means or does mean. In cognitive science, connectionism is an effort to reproduce intellectual abilities of the brain by brain models. These are known as artificial neural network or neural networks. Neural networks are simplified models in that sense that they consist of a large number of units, analogs of the neurons, but restricted representation of the neurons, and using weights that measure the strength of the connections between the units. These weights model actually the effect of the synapses that link one neuron to another. Experiments or models of this kind have demonstrated an ability to deal with many application problems this way, and that is why connectionism became a kind of ruling paradigm in artificial intelligence research. So if we go further with the concept of neural computing, the first thing to mention is that neural networks are not programmed to perform a specific task, but they are learning by example. So practically, the overwhelming majority, I must say, neural networks need some sort of training. The network is composed of a huge number of highly interconnected processing elements. These are dubbed as neurons, and these work parallel to solve a specific problem. Training by example is needed, as I mentioned, and it should consider the problem at hand and to define the type and amount of data needed. So there is no general type of training of neural network. It always depends on the problem and the available and providable set of data. In case of improper, under or overtraining, the network might be functioning incorrectly and useful time may be wasted for the reason that obviously then the data should be modified or even the neural network should be adapted. The network itself finds out how to solve the problem and its operation may be unpredictable. So every neural network, in a sense, is a black box, and we cannot monitor how the neurons are working. Important aspect from the point of view of computational support that the need for computational power grows exponentially with the complexity of the neural network. Simply put, it means that the larger our neural network, the more elements are included in the network and more connections are activated in the network, the higher is the need for computational power. Neural computing developed over quite a long period of time. So actually, the endeavor to develop various solutions is with us since the very first appearance of the idea of artificial intelligence. The remarkable stages, milestones are indicated here on this diagram. And you can see that in average, in every 5 years, a new idea popped up, which in a sense revolutionized our thinking about artificial neural networks, either for the reason because they provided new computational opportunities, or they were placed on a different scientific principle or scientifically studied basis. So very briefly, it started with the simply neural net of proposed by McCulloch and Fitz, and then it goes through, for instance, the reception or the perception model of Rosenblatt, then the XOR network, which were studied extensively by Minsky and Pepper. These were also important milestones. And the Hopfield network can be mentioned as a next significant achievement. And then the recurrent neural network, for instance, and different variations of that. And then the deep belief network from Hinter, and then the long short-term memory concept proved up, and then the deep Boltzmann machine, and for instance, very recently the capsule networks and the GIANs. I will illuminate on or elaborate on it later on. Popped up. So these are the major historical developments. And what we have at this very moment is an arsenal of various types of neural networks. Actually, I am not aware of any exhaustive categorization, but definitely the literature is discussing many types, like the perceptron model, the autoencoder model, the neural Turing machine, the radial basis function-based neural network, the multi-layer perception model, the long short-term memory, the deconvolutional network, the liquid state machine, extreme learning machine, recurrent neural network, echo state machine, generative adversarial network, deep convolutional network, and deep residual network. Obviously, these are important, or here in this bullet, there are important information about what they mean. Here is a kind of legend to associate the color coding with different meaning. You can study it more extensively in a paper which was published in 2021 by Gundel and co-authors under the title Neurocomputing. Actually, I also used the information from this particular paper for this overview, what I'm showing here. Obviously, it is not possible to discuss this variety of neural networks. I will focus on later on only 3 of them, which we believe has an importance for smart cyber-physical system development, because they are having certain operational characteristics which make signal processing easier with regards to cyber-physical systems. So if you are talking about neural networks, as you can see, they are already they are computing programs that are based on associative theories of human cognition. As electronic automatons, they are similar to cellular automata in that they offer simplified model of the brain. Various algorithms use different connection topologies and different weightings between the neurons. The connectivity allows to capture a pattern, such as learning a voice or recognizing a visual pattern. Every neural network has an input layer, at least one hidden layer, and one output layer. You will see later on that actually this is a rather classical minimalistic approach, because the modern neural networks were extremely large number of layers, or even leave behind the concept of layers and focus on purely connected neurons. The overwhelming majority of the most applied real-world machine learning is happening with the set or using the strategy of supervised learning. And then what everybody knows is that neural network can be used for machine learning tasks, and neural networks treat the computational units in a learning model in a manner similar to the human neuron. Rosenblatt's perception algorithm was seen as a fundamental cornerstone of neural networks. Nowadays, data hungriness and computational intensiveness of neural network is a kind of partially solved problem, but earlier it very much influenced their applicability. Neural networks are theoretically capable of learning any mathematical function with sufficient greater training. So the transfer through a neural network can be rather arbitrary. Some variants of neural network, like recurrent neural networks, are known to be Turing complete, simulate any learning algorithm given sufficient training data. But I have to mention here that, for instance, the major achievement with recurrent neural networks, that they also use so-called pseudo layers in order to amplify their operation. If we consider applications of neural computing, then we can mention, for instance, sophisticated web search engines, which are strongly based on neural computing. We can also mention advanced text-to-speech conversion algorithms. Then typical application of neural computing is context-based advertisement planning. Many internet-based sellers are using these sort of techniques. Then neural computing is also used in near human level image classification. This is actually a booming field because of the density of information is in visual images. It received a huge attention, and actually many of the neural network developments are pointing to image classification problems. But neural computing is also very useful in answering natural language questions. They can synthesize semantic answers to questions posed by humans. Then near human level speech recognition, so interpretation of the speech, even identifying emotions, hiding or implicit context in speech is possible nowadays. Then superhuman chess and Go playing. We are all aware of this, that actually neural computing beat the best of chess players and Go players. Then also near human level text transcriptions. So translation from one language to the other is also using neural computers nowadays, and there are quite effective solutions on the market. Then near human level emotion detection. This is a very rapidly developing field. Started with face recognition, for instance, but nowadays it is supplemented with other techniques as well. Then sophisticated machine translation problems are addressed, and complex situation analysis problems can be attacked with neural computing. And personal digital assistants have been developed based on neural computing. And from our point of view, is important that also smart problem solving with cyber physical systems is heavily addressed in the literature by neural computing, and there are many interesting proposals for using neural computing technologies in cyber physical systems. Coming to the end of this first block, which was about the human-related fundamentals, let me suggest a couple of literature sources for you to extend what we have discussed until now. A almost 25 years old paper is the first one, what I would like to recommend you, and this is related to the Human Brain Project. I don't know if you remember, if you are aware of this very pioneering and road paving project. Actually, it was existing for several years and produced remarkable results. So in this particular paper, the people who were involved in the project actually summarized their findings related to neuroinformative tools for integrating searching and modeling multidisciplinary neuroscience. Very seminal and thought-provoking paper. The other one, or the next one, is a book authored by Amit and published by the CRC Press. It is Artificial Intelligence and Soft Computing. behavioral and cognitive modeling of the human brain. Very relevant for the discussion what we had for the presentation what we had until now. And then the Domenico paper on multi-layer modeling and analysis of human brain network is a relevant paper. And then the Sharkey authored paper on connectionism, the computational implementation and utilization of connectionism is detailed in this particular paper. And the last one is about neural computing, the general fundamentals and approaches. This was one of the papers which I refer to in the meantime. This particular paper is very remarkable from the point of view of surveying what was available in 2021 and what the different approaches mean and how they differ from each other. So this concludes the first part. As I mentioned, it was a kind of introduction to the basics. When I lectured to students here about neural networks, they were always pleased with knowing a little bit something about how the implemented neural network models connect and how much they can represent with what fidelity they can represent what is going on in the human mind when we are making reasoning and learning. So that's why I thought might be interesting for you as well. And then I'm turning to the chairman. Maybe we have any comments or some comments or questions. Do we?
Anybody having any comment, any question? Anyone having any comment, any question?
Thank you so much. I believe then we can continue the discussion, and I continue with the second block, which is about the neural reasoning mechanism from a kind of more technical perspective rather than a historical overview perspective. So the neural modeling, as I mentioned, starts with the modeling of the elements of the human brain, and our task is simply to convert it into something which can be processed by computational structures. So here is a direct mapping to a computational model of what one neuron represents. And here, obviously, there are input channels which are substituting the bandwidth, and there is a kind of summation. And when the level of the summated input signal reaches a particular level, a threshold level, this is when the neuron is firing. And then, as a result, a kind of transfer takes place to other neurons which receive this information and working further on this. So this is the simplified neural modeling of a neuron. And obviously, the task is to convert or to aggregate these sort of simple representations into complex architectures, complex neural architectures. So when we want to combine neurons into networks, it has to be seen that a neuron can implement practically any type of logical gate, for instance, a NOT or AND or OR none type of gate. The network of the neurons is actually a network of logic gates in this interpretation, and this simplified representation is called the new network architecture. The arrangement of the neurons in a network influences how the learning algorithm finds the biases and the weights. The typical 4 steps for network creation are the aggregation, the remix, the repurpose, and the feeding. These are extensively discussed in the literature. The artificial neural network architectures are based on 3 criteria. First of all, the number of layers, which is a variable. Then the flow of information, that is how the neurons are connected and how they are passing the information from one to another. And the other one is the neuron connectivity, which means actually a functioning on the connection, how it is happening in the real life. That is important from the point of view of the neural network architecture. There is no best network architecture. So earlier I already mentioned that the fact that something appeared recently doesn't mean that it can solve everything. It is simply a kind of refinement, a enhancement, most probably, of what was already practiced in the past. So typically, the neural network architectures are neuron arrangement defined by the computational purposes, and we have to select them accordingly. When we are getting to neural networks, then we have to just go through those ideas that they are providing only a rough abstraction of the human mind and the neurons included. They work as input-output transformers, so receives input signals and weight, and they sum up the input, and if the input is big enough, then there is an output signal fired. So mathematically, for the simplest network, the summation procedure and firing procedure can be represented with a simple figure as like this. The other thing is that the non-continuous step function is typically used, and there are different approximations because this sort of transfer is substituted, for instance, by this asymptotic transfer function. And this sigmoid curve, for instance, which is used for a long time in various neural network architectures, is mathematically modeled by these functions, and also this is a continuous function for which there is a derivative in the form which is shown here. So if we see how the architecture is built up, and if we consider the fact that different numbers of neurons may be included, and different relationships can be generated between the neurons, then we can go into a classification of the architectural aspect or the architectures of neural networks. Actually, we can have already a single static neuron network. The neuron which I showed earlier can be activated, but obviously what it can do is very simple learning tasks. If we want to extend this capability, then we have to couple the neurons, and this is the second architectural class, the coupled static neuron. Then obviously we can have multiple static neurons and multiple dynamic neuron relationships. The static and dynamic relationship may be included in a single static layer or in a multiple static layer or in multiple dynamic layer architecture. So these are the three typical architectures on a higher level: single static layer, multiple static layer architectures, and multiple dynamic layers. Based on which we can identify single structure neural network or compound structure neural network. And actually, this is the scheme how we can oversee all types of implementations of neural architecture. So the number of layers, as I mentioned, plays an important role. And looking at how many layers a neural network has, they can be divided into so-called shallow networks, deep networks, and composite networks. A shallow network consists of three layers, which are named input layer, one hidden layer, and the output layer. The input layer doesn't really consist of neurons. It is more a kind of collection of input ports through the input information values are transferred to the network. So it's the only function.
Yes.
Hello?
I think your slides are not coming. You are.
Hello?
Yeah, am I audible?
Sorry. Hello?
Yeah, am I audible?
Hello?
Yes, sir.
No, Imre, I'm just asking to Imre. Imre, am I audible to you?
Oh, yes. Now I can hear you. Yes. Yes, please.
Your slides are not coming actually since you broke actually.
There is no sound.
No slides. Sound is okay, but slides.
Oh, what happened here? Then, because again, the problem with the slide sharing at the very beginning.
You have to stop it and.
I go back to the and reactivate the slide share because this is how I started. That I started to share the screen.
Now it is coming up. Yeah, now it is screen has come. Emily, you're muted. Unmute yourself.
I didn't do anything, and in the meantime, there are no slides. Sorry for that. Sorry, there is a problem in the communication today. I apologize. I did everything according to what is needed to do. I shared the screen again. I even told it, if you remember. So then let me show you the slides, what I presented until now. I'm sorry for this. This was the first slide, and then this was the next slide in which I explain how the neurons are combined into network, and then this was the slide on the basic operation is the neural network. This was the slide on the architectural classification. This is the slide on the number of layers which are actually started to discuss. And then I go to presentation mode, and please be so kind to confirm if you can see the presentation now. Can you see the presentation?
Yes, sir.
Yeah, it is coming now. It is come. Number of layers.
Thank you so much. Thank you so much. I go further then. So actually, I mentioned that we can differentiate shallow network, deep network, composite networks, and the shallow networks are typically 3 layers, but in fact only 2 active layers. They are operating on the hidden and the output layer because these are what actually contribute to the learning. So the input neurons are actually ports and not having any kind of cognitive role there. The computational model of the network represents each layer by two mathematical vectors, one for biases and one for weights. According to how information flows through a network, artificial neural network can be divided into feed-forward networks, which are propagating the information continuously ahead, and a recurrent network in which there is also a backward propagation effect. It is not overall, it is typically local in recurrent network. So the topic of recurrent neural network was mentioned, and then let me go into this particular type of neural network, and let me give you a brief explanation why I believe that from the perspective of cyber-physical system, this category of neural network has significance. Namely, earlier we discussed that cyber-physical systems actually typically receive time sequence data, and we are often producing data sequences which are related to subsequent events. For instance, in home care, the sound detection plays an important role, because when you record silence, then you know that most probably nothing is happening. When you hear a noise, it might be an indication of the event, and then the continuation of the event indicates that what is actually happened or what might happen, and so on and so on. So what is important here that you cannot reason with the cyber-physical system about a currently detected noise if you don't know what happened beforehand. And this is what the recurrent neural network allow us to manage, namely certain kind of temporal sequences in input information. And the recurrent neural networks are a type of artificial neural network where the connections between the nodes are able to follow a particular temporal sequence and adopt the learning procedure to that. Most often than not, recurrent neural networks are represented as a directed graph that includes the temporal component. Recurrent neural networks can contain cyclic connections that allow them to remember things from prior inputs when generating the output. I just try to explain the importance of this in the context of cyber-physical systems. And the recurrent neural networks can process sequential data effectively and use their internal state or memory to process each input sequence. A recurrent neural network classifier or recurrent neural network classifiers have multiple multi-layer architecture where each layer learns a different representation of the input data, and they add up to what they have learned. This characteristics makes recurrent neural network classifiers flexible for application to multiple text mining tasks, for instance, but also, for instance, sound analysis tasks, what I mentioned earlier. But here there is something which is a implicit important statement, that they are typically classifiers, and they can make classification without needing task-specific feature engineering, which is an important aspect from the point of view of economy of using this particular type of network. Recurrent neural networks deal with words also, or can deal with words in text step by step and deliver the current hidden information to the next step in the network with the same structure simultaneously, and this way contribute to the interpretation of the text. If we would like to visualize the operation of the recurrent network, then here is a simplified model. The inputs are here, and there are different time steps defined for the network. It can be quite large, but it can be also just very limited. Depending on the number of the time steps applied, the more information can the recurrent network consider in the learning procedure from the previously learned element. So there is a memory layer actually, or multiple layers, which are identifying patterns over time. And there is a so-called decision layer in which actually the classification is taking part. What is a unique feature of the recurrent network that actually with this sort of operation, we have a attention mechanism here, a attention shifting mechanism, which shifts the attention of the nodes or of the neurons in the memory layers to the newcomer information, and they combine it with the already received information, and this is how they come to the decision. Recurrent neural networks are the kind of feed-forward neural networks, so actually they stream the information front, and they are capitalizing for this reason on the concept of the multi-layer perception. The general flow of data and the mass of vague connections between each layer play an important role. In a forward pass, each neuron gets some input data, thus the computation feeds the output data forward to the next layer. The input layer feeds the hidden layer, and the hidden layers feed the output layer. With the recurrent neural network, connections are no longer purely feed-forward, however, because the recurrent connections are breaking up the pure feed-forward rule, which is typically in the case of multi-layer perception models. So the recurrent correction means that outputs of certain neurons of the output layer are fed back to the same or the other neurons of the output layer. So there is an additional recurrent connection feeding the same output back into each neuron. This was a brief overview on the recurrent neural network, and let me elaborate a bit on the extreme learning machines, which are also playing a role most probably in reasoning and learning with the cyber-physical system, because actually they are focusing on the capabilities or the utilization of the capabilities or individual neurons. Let's see what does it mean. So the assumption of extreme learning machines is that effective learning algorithms can be derived based on randomly generated hidden neurons. So actually in an extreme learning machine, not all the neurons are defined before the training takes place, but when the network is working, there are opportunities for randomly generate neurons, which will be located on the hidden layers or connected to the or placed connected to the hidden layer. So evidence from neuroscience suggests that similar principles are applied in biological learning system as well. In extreme learning machines, the hidden neurons need not to be tuned since they are inherited from their ancestors or randomly generated. The neurons are nonlinear piecewise continuous, independent of the training data and the application environment. Learning theories and practice prove that extreme learning machines are to predict reliably with a near zero error for large populations when you have large amount of training data. Extreme learning mechanisms are fairly robust with regards to the mapping function and the number of nodes in the hidden layer. Other characteristics of extreme learning machines that they are very flexible deep learning architectures. The flexibility of the extreme learning machines allow for supervised learning, unsupervised learning, and semi-supervised learning. This is an important characteristic. They have mathematically proven universal approximation properties that have to do with random sampling. They are relatively fast to train without back propagation. Extreme learning machines fit in the same way as multiple regression models do. In contrast with deep learning, they do not require extensive tuning and building of architecture. Later on, I will talk about this issue. Extreme learning machine may be one of the fundamental learning practices filling the gaps between machine learning and biological learning, of which activation functions are even unknown. The other category, what I would like to bring up is the so-called GIAN or generative adversarial network. Let's look into the major characteristics of this type of network. The GIAN models were proposed as a great breakthrough method and have been extensively applied in image generation field. The generative adversarial network contains two neural networks in one. This is from the reason why the word adversarial is used in the name. So one of the neural network is the so-called generator, and the other one is the discriminator, which contest with each other under the principles of the game theory. So the generator commits to generating fake data to the point of confusing the discriminator to mistake them for real samples in the training set. And then the discriminator is responsible for distinguishing between the generated fake data and the real samples. During the training loop, a batch of fake data is generated by the generator, which is used then subsequently for training both the generator and the discriminator. This is accompanied by a training loop with real data. So the first action in training generative adversarial network is teaching them with partly fake, partly real data. And then the next refining loop is working with truly real data. The objective functions were originally defined as two parts for G and D respectively. Another type of neural network architecture which has relevance for consideration in cyber-physical systems is the short-term, long short-term memory. Sorry, it's a complicated name, in fact, which are also working with temporal aspects. So a long short-term memory network is an alternative to the regular RNN and can handle long dependency. This classifier is suitable for complex text processing tasks where sentences are long and descriptive. In the last years, the use of long short-term memories to perform relation extraction tasks has become widespread in many domains. Bi-directional LSTMs were introduced that use two LSMT layers at each computational step. One of them reads the sentence from right to left, and the other reads the sentence from left to right. The combined output of both layers produces a final score for each step. So the bidirectional long short-term memory can yield better results than traditional long short-term memories when applied to the same data set. A new element of the current working with neural network architectures is the trained network transformation issue. And the LSTMs are which are associated with time series and sequence data are a typical example when the trained network can be transformed. The transformation in this particular case means a transfer from classification operation to clustering operation. And behind this is that the LSTMs remember some portion of the data prior to making the current decision. I mentioned that the conversion can be made from classification to clustering, but it is a kind of playing with the various architectures. And the architecture, which is typically used for classification purpose, include a sequence input, the LSTM, a fully connected layer, a softmax layer, and the classification layer. Whereas the architecture for regression includes only 4 elements of it, namely a sequence input layer, the LSTM layer, a fully connected layer, and the regression output layer. So if we want to transform a trained network, trained LSTM network, then what we have to do is to replace the output layers, for instance, the softmax and classification layer, which is used, for instance, in MATLAB for classification purposes, can be replaced by a regression output, and it can be defined into the network architecture model. It means that only the classification output layer should be changed to a regression output layer, and then you can use the same data what you already applied in training the network for a different purpose, to regression instead of classification. Obviously, if the data are seen in context before the training is, before they are used for the training, it allows to have a better set of training data, which in turn offer the opportunity for better association, which plays an important role, for instance, in speech recognition. This chain opportunity in the output layers of the neural network architecture led to the concept of transfer learning. Transfer learning is a methodological approach to convey knowledge from one particular trained neural network to the other one. Transfer learning is aimed at reusing pre-trained models built by experts in resembling an application. So the models which are built and consolidated by experts can facilitate the work of the less experts in developing or creating neural network structures for their application. An example, as an example, AlexNet was trained, for instance, on 1.3 million high-resolution images to recognize something like 1,000 different objects. The model processed by AlexNet can be retrained to perform new recognition tasks. An accurate transfer learning can also be achieved with much smaller models and datasets and intense modifications of VST. One example is Google Maps, which is most commonly used, which is one of the most commonly used CNN for image classification, trained with more than 1 million of images so far. It can classify images into 1,000 different categories: keyboard, pencil, dogs, cats, horses, and so on. Other animals are advertised as representative categories. Important is that no specialized pre-training for professional applications are needed. Let's elaborate on the concept of transfer learning a bit further. So it is an approach that amplifies knowledge of one type of problem to a applies knowledge from one type of problem to a different but related problem. I mentioned this example of Google LMS, which can be trained through transfer learning for objects not trained in the original network. In this case, the last 3 layers of the network are to be simply trimmed off and to be retrained with other own images. This and then obviously they should be placed back to the network architecture. This approach produces the most accurate results, but it generally requires thousands of labeled images. Such training also needs considerable computational resources and a reasonable level of automation. A good strategy for transfer learning is to try choosing one of the faster networks, such as SqueezeNet or Google Net. In transfer learning, if transfer learning doesn't make the VLM to see an application, then an own network needs to be generated from scratch. A practical approach to shorten the training time and to make the knowledge transfer efficient is a kind of transfer between multiple nets, and some nets are mentioned here in my presentation: Google Nets, ResNet, and SqueezeNet, just to name a few, which are offering themselves to architecture modification and this way knowledge transfer. The accuracy, speed, and size are all important issues here, and obviously there is a trade-off issue choosing the original network and then modifying it to an application, which is typically a kind of compromised problem. And then you can find a MATLAB plot that compares the image net validation accuracy with the time required to make the transfer. I apologize for this delay, but at the very beginning we experienced a technical problem. Let me close this block with and the end of the presentation with the suggested literature again. Goodfellow and Cole's papers on generative adversarial networks is the first what I would like to suggest. And the other paper is dealing with recurrent neural networks, what I propose. Then here is a paper about long short-term memories. And the other paper is about how to use confusion matrix-based feature selection in order to improve the training. And then there is a paper here which talks about the three-way confusion matrix for classification, and it is a kind of measure-centered approach. So as a conclusion, I would like to remind you that the first block tried to give a overview of the issues of neural modeling of the human brain. The second block focused on some elements of the neural reasoning mechanisms and also some important implementations, important from the point of view of using inside of the physical system. It also introduced the concept of transfer learning as a new methodological support for cyber-physical system developers. This concludes the first lecture. I stop here and kindly ask you if you have any comment, any questions related to what was presented. And again, once more, I apologize for the delay and the technical problem I wasn't aware of. I just tried to share the screen as well.
Anyone having any question?
Yes, sir. Good morning, sir.
Good morning.
Sir, yes, sir. I have a question.
Please.
Sir, for audio classification, CNN and RNN both are used at that time. For in the case of CNN, we use spectrogram as an input for the classification, and RNN I have directly input the audio signal. So for the better classification, which method is best, RNN or CNN?
I don't know the answer this way. I have to confess that it would be too much for me to say that this or that. I have to go deeper, and we have to go deeper into the analysis of the problem. What is the major objective, please? This is I apologize for asking back, but what is the major objective?
Sir, my objective is to classify the audio signal or classify the features of audio signal.
Classify.
So we have two methods.
Yes, but
yes,
okay, it is an important piece of information for me. So actually, what you want to do is to classify audio signals based on recognized features.
Yes, sir.
And what is the purpose of the classification? How you want to, because obviously the classification is just a means to get to some knowledge. What is the knowledge what you want to generate, and how do you want to use it, please?
Sir, actually, I am working in the biomedical field. So
okay.
I have different person have different frequencies, amplitude and pitch. Their features are different. So I have to classify their features with the help of machine learning algorithm.
very, very clear. So actually, the sound analysis is or voice analysis is related here to the context of medical application, as I understood. And this
Yes,
is
sir.
this underlines anyway the importance of understanding the context, because this is why I had to ask back, because the question was clear, but the context not. And then, sir, let me ask you, and to help you a little bit further, have you made comparative studies with the two approaches, what you mentioned? Because this is what I would do, and this is what I would recommend to my students to do. You know, if you have these two techniques, if you maybe you use MATLAB.
No, sir. No, sir. Python. I have used Python.
Python or Python. Okay, but there you can have the two mechanisms ready. And then you can use the same input data set for the two for training. And then
Yes, sir.
you can see how they behave, and then you can compare them. So I understood the problem, but without really seeing that what is taught, how many data are used, how much the data are really relevant with regards to identifying the features of the sound recording and these sort of things. It is very difficult to give a ex cathedra answer. However, if I may suggest you, if you want to deepen in this problem, then make a quantitative comparison. Make
Yes, sir.
multiple training and multiple application loops and record the data systematically, and then see how the variation and what type of variation happens. I believe it is actually in that particular unique context in which you are working, it can be a basis for you for publishing a paper. And I would like to encourage to do it.
Okay. Thank you, sir.
So this
I
is
have to do it.
I sorry for refraining myself for saying that which one is better. I still don't have. I mean, the information what I have at this very moment is not enough to make an conclusion. Thank you for the very relevant question anyway. Appreciate it.
Okay. Thank you, sir.
Any other question anyone has?
What I would like to suggest to you, if you are interested, please really study this sort of knowledge transfer issue between different neural networks. And also, I believe this sort of the new developments in the field of modification of architectures for certain purposes. It is really something which provides you new opportunities. So please look into this aspects, the modification of neural network architectures, for instance, and this sort of transfer learning between various architectures. Thank you so much again. I apologize for this re-explanation of my point.
Okay. Thank you, sir. Thank you for guiding me.
Thank you.
Okay.
Anybody having any other question? So if no question, I request all of you to kindly switch on your cameras. We'll have, as usual, one quick click. So all of you, please switch on your camera once again. Swati, Ruchika, Vivek. Swati, Ruchika, Vivek, Anand. Vivek. Okay, all of you smile, please. Don't be so tense. Okay, so unfortunately, we are not left with much time, but still, Emre, how do we do? We are left with only just 1 minute because the session got.
Yeah, let's shorten 5-10 minutes or 5 minutes is enough, and then we can go further and maybe
We'll take a break of 5 minutes. So we'll reassemble by Indian time at 3:20. That will be 6 minutes break, and we'll try to finish the next session earlier. Am I right, Imre?
thank you so much. I really
All of you should be here by 3:20.
thank you.
Thank you, Imre.
If you think, colleagues, we may start.
I'm sorry. I was speaking without noting that my mic is closed.
Yes, the recording is on.
Just record. So all of you are there. So let's start the second session. Yes, sorry for this short break, but okay.
I hope that you can see the slide
Yes.
now.
Yes, they are visible.
Excellent. So this second lecture is about the deep and convolutional learning mechanism. Obviously, I cannot go so deep as programming implementation, but I would like to summarize the main characteristics. If we look into the overall developments here, then we can say that first we had the so-called traditional learning mechanisms. Then the machine learning mechanism represented a subset of that. The deep learning mechanisms, again, a subset of the machine learning, and the extreme learning mechanisms are a subset of the deep learning. This is how the general image is, and this is what we have to know about the relationship, about the various approaches. So the computational learning has the machine learning approaches and the deep learning approaches. The machine learning approaches were identified as, for instance, unsupervised learning, semi-supervised learning, supervised learning, and reinforcement learning. Here in the field of deep learning, we can identify unsupervised pre-trained learning, convolutional deep learning, recurrent deep learning, and extreme learning. What is between them is three characteristics, namely that while machine learning needs manual feature identification, deep learning has automated mechanisms for feature extraction. The second improvement is that deep learning structures, architecture, use a cascade of multiple non-linear processing layers, and that enhance their computational capability. And deep learning having many layers, even output layers or close to output layers, offers the opportunity for transfer learning. So let's see the principle of deep learning. It is a computational learning approach that teaches computers to learn by examples, which is a natural thing for humans. Deep learning is a key technology behind driverless cars, enabling them to recognize a stop sign or to distinguish a pedestrian from a lamppost. Deep learning is the key to voice control in consumer devices like phones, tablets, TVs, and hands-free speakers. Deep learning is getting lots of attention lately since it's achieved results that were not possible beforehand. Deep learning learns a computational model, which is actually an implicit problem-solving algorithm to perform classification tasks directly from images, text, and sound. Deep learning models are trained by using a large set of labeled data. The data are typically labeled by the algorithm itself, and the neural network architecture that contains many layers. Because there are several useful short videos from, for instance, the networks company on the internet, let's enrich our presentation with a short video which is talking about the first steps into deep learning. So now I stop with the presentation, not with screen sharing. So hope you can see again my desktop, and you can see this particular movie what once we received from the network.
In this video series, we'll help you understand why the sequential chapter process. What is deep learning? How is it used in the real world? And how is it extended? So what is deep learning? Deep learning is a machine learning technique that learns features and tasks directly from data, whether they use images, text, or sound. In this video, I will use images, the most complex thing we use for other types of data. Deep learning is often referred to as scientific learning. So let's take a look at an example. Here are the set of images, and I want to recognize which category of action each image belongs to: sound, text, or voice. I start with the output of the block. Algorithm moves from grammar by prepared algorithm with specific features and objects in the image. The design algorithm then learns how to classify input images into the desired categories. We use the term encoding learning because the process learns directly from data. Another example is a robot learning how to compare the movement of its arm to pick up a specific object. In this case, the task will learn is how to pick up an object moving against the image. Many of these techniques used in deep learning today have been around for decades. For example, deep learning has been used to recognize hundreds of processors in the data since the 1990s. The use of deep learning has changed over the last 10 years, primarily with the three factors. First, deep learning methods are now more accurate than people at classifying images. Second, GPUs enable us to browse and reduce records in real time. And finally, the rise of integrated data requires for deep learning has become accessible over the last 2 years. Most deep learning methods use neural network architecture. This is why we often use deep learning models to transfer smooth neural networks. One popular type of smooth neural network is known as a convolutional neural network, or CPS. A CPS is successfully executed for working with image data. The term loop usually refers to the number of images in the neural network. When traditional neural networks only contain 2 or 3 hidden layers, some learning can deep networks have as many as 150 layers. So now that we understand these two deep learning concepts, here are a few examples we can try with MATLAB. Recognizing that MATLAB classifies objects on my desk. And this
Now I would like to continue with my presentation. Please be so kind to confirm that you can see the presentation. Can you please hear the presentation? Can you see my desktop?
Yes, sir. Yes, sir.
Thank you so much. I wanted to make sure that there is no technical problem again. So here is a concise overview on the essential characteristics and application opportunities of deep learning. So everything is fine. It can be summarized in 3.5 minutes. So we have nothing else to do. Let's go home. Obviously, if I'm saying it, then I have a purpose. Namely, the purpose with this is to call your attention that you have to be aware of several technical issues related to deep learning, and that will be summarized in the follow-up slide. So what we heard is that the deep learning is a kind of second resurgence of neural network research. Some say just a new trendy name for neural network research. There is something in that. The other objective of this genre of machine learning algorithm is that use a cascade of multiple nonlinear processing layers, learn different representations of the data in each layer, and derive high-level features from the low-level features. So deep learning algorithms implement various complex model structures to form a hierarchical representation of the data. There are high expectations, as you heard in the video, towards deep learning, and though techniques used in deep learning are inspired by neuroscience, deep learning is not an artificial equivalent of the human brain yet. So the major characteristics of deep learning are that they became useful for the capabilities of handling large amounts of unlabeled and labeled data, and substantial increase has been achieved in terms of the computing powers, and nowadays we can use, for instance, parallel graphical processing units for powering processing of deep learning networks. And when combined with cloud or edge computing, this enables reducing training time from weeks to hours. This is what I typically see in the literature written, but on the other hand, I believe this statement is a highly conditioned one. The relevant features are not retained but learned while the network is trained with a collection of the images. Obviously, contrary to this fact, I mean that the system automatically tries to learn the features. A lot depends on the input data, how they are representing the problem and how they are structured. So if we go back what the deep learning architectures are doing, actually the last layers learn how to detect more complex feature of the object it is trying to recognize. And these layers can be made manipulatable, editable, replaceable, linkable. This is actually what is important here to know or to remark, that the transfer learning principle can be also used for deep learning technology. The deep learning networks are represented by algorithms, as you heard by the gentleman in the movie, like convolutional neural network, which, according to my view, is just a subset applied in image processing field. But there are other deep learning network architectures and deep learning mechanisms to mention. For instance, deep learning has been extended to the field of recurrent neural networks, and establish connections that keep track of previous information to make future prediction was the goal. Long short-term memory network, special type of the RNN used for sequence and signal data processing. Generative adversarial networks, we heard about it. They can generate new data based on existing data, avatar traits from human, for instance, an example for that, and the extreme learning networks which use runtime generated neurons to optimize learning quality. So there are plenty of implementations of deep neural networks, and many of the concepts were imported from the traditional field of machine learning. However, as I mentioned, there are a couple of technical issues to the development and use of deep learning architectures and mechanisms. So they, first of all, act as feed-forward neural network architecture, and as such, they are universal approximators. They approximate any function with arbitrary low error if they have sufficient number of neurons and layers, and the learning conditions may result in a massive overshot. So they sufficient, they can generate sufficient number of features for the recognition afterwards. The number of required units in the input is exponentially or grows exponentially if we want to increase the quality. And if the network has at least k number of hidden layers, in other words, if it is deep enough, then the number of neurons required for approximating the activation function is polynomial in the input. So this is a computational issue. It has been shown that there exists a k number for certain activation functions which can be used for the deep learning networks. And deep learning networks have a lot of hidden layers arranged in hierarchy. So it is not arbitrary, but the processing is typically based on certain kind of hierarchical arrangement. And this is the way how they learn from complex data. Other set of technical issues are that, as the gentleman mentioned, that the deep learning networks are developed for providing start-to-end solution for problems, which means that you don't have to do anything, just this is the expectation and this is the strive, that you don't have to do anything, just take an already trained deep learning network and use it your program, and you will have your result. At this very moment, though it is a relevant assumption, it doesn't work completely like this in the practice. Deep learning networks generally need more data to perform well with respect to traditional machine learning algorithms. So every deep learning is computationally intensive. You heard that actually we have to consider exponential growth in the need for computational time. So to finish the sentence, the deep learning is computationally intensive due to the high number of matrix multiplications which are to be done. It needs high-end machines for better performance when compared to traditional machine learning, and that's why the issue of using cloud computing or edge computing for this purpose was raised. But please don't forget that both have overheads, and it is not a direct improvement of everything. Deep learning networks takes more time to get trained, and the consistency of the data remains an important assumption. But on the other hand, it is a positive thing that it is possible to transform a deep neural network trained for classification to regression. I showed earlier what are needed there. The third block of the technical issues is that though the deep learning networks were proposed in the late 60s, even the last efforts couldn't eliminate certain issues, such as, for instance, the vanishing gradients issue. If the transfer value is too small or too big, the gradient becomes near zero and not updatable. It is possible that large part of the network stop changing, and there is a kind of freeze situation with the network, which limits further learning. Then the saturation issue, which is often mentioned in the literature, that the absolute value of the rated inputs is large, and the gradient goes to 0. In that case, there are no updates, and it means that the learning capabilities of the deep learning network is again limited. Overfitting, earlier we were talking about this concept. It is also related to the deep learning architecture. So high model capacity prone to overfitting and showing tendency of early stopping. These are the observable characteristics of overfitting. And then the convergence, which is an issue with getting stuck and losing the sensitivity to learning intensively. So an approach to overcome most of the above issues is the layer-wise training, which is often called stochastic gradient descent. Let me very briefly summarize what are the main elements of a layer-wise training. Obviously, the objective is to avoid or reduce saturation of the activation function. So it can be achieved in a particular process, which includes the following steps. First, train the network with single hidden layer where the desired output is the same as the input. The second, cut the output layer. Since we have editors for deep learning structures, with the editor we can do this. Then train the new network with a single layer using the hidden layer of the previous network as the input. And the fourth one, repeat from action 2 for some more layers. And finally, for supervised learning, put a final layer on top of this structure and optionally fine-tune the weight. So here is a symbolic figure which indicates the fixation of certain layer and operating with some active layer. Here comes also the issue of feature engineering to the scene. Feature engineering is defined as the process of extracting important features of data using domain knowledge and then feeding them into the learning algorithms or mechanism. This process ensures that the patterns in the data are more recognizable by the learning algorithm. For traditional machine learning algorithms, the traditional problem should be broken down into smaller parts. The crisp distinction between machine learning and deep learning comes from the fact that deep learning structures are typically equipped with some sort of automation of feature engineering. Most of the applied features need to be identified by an expert in the traditional case, which requires a substantial time and effort. The goal to develop sophisticated deep learning architecture is to spare this time and effort. And it can be achieved by the fact that the deep learning network would extract the features on their own. Obviously, there is a reliability to the extracted feature and the relevance for this extracted feature set in the application, but these are all issues which are really related to the discipline of feature engineering. There are various deep learning network architectures, and as combination of layers, they reflect what the every architecture is designed for a particular purpose, and a network architecture also defines the way in which the deep learning model is structured and developed. Architectural determines the accuracy of the model, what the model can predict, what the model expects as input and output, the combination of the layers to realize learning, how data flows through the layers. I mentioned that currently it is mainly considered in image recognition and image generation. And the architecture of the network is one of the many factors that impact changeability. Something about the both interoperation of the deep learning mechanism. So importing and exporting parts of networks is becoming a design and structuring issue. There are different initiatives, for instance, the Open Neural Network Exchange initiative, which propose a novel intermediate model format. This ONNX supports the interoperation with other trained deep learning network frameworks such as the Tensorflow, the PyTorch, the Computational, Microsoft Cognitive Toolkit, CoreML, and Apache MXNet. ONNX model format is also support exporting the data. Networks and network architectures can be imported to MATLAB from TensorFlow, Keras, so TensorFlow 2, ONNX, and Profit. MATLAB supports exporting the chain deep learning toolbox network or a graph of networks layer to the ONNX model format, using the export ONNX network function. The process of reusing pre-trained deep learning networks is composed from the following stages. The first, load the pre-trained network. Then the second, replace the final layers. Then retain the modified network. Then predict the network accuracy. And then test the retained network with additional images, and then predict the final accuracy of the network and see the various probabilities after deploying the results, and further improve the network performance whenever it is needed. So the best practice, what I can suggest it to you for the time being, is combining machine learning and deep learning. If you combine machine learning and deep learning, we will end up with a kind of hybrid learning. But what is important with regards to hybrid learning is that it is not only a combination of the best capabilities, but it also provides you an opportunity to use deep learning as a feature extractor, which where it is based on the automation and the high level of accuracy has superiority, and to use machine learning to create the classifier, because in certain cases it can achieve better results. There are several applications of deep learning. You heard in the video, and also I was talking about many applications. At the end of this block, let me propose you a couple of literature sources. The first one is actually from MathWorks, from the latest package. You can read about, you can read an introduction into deep learning with MATLAB. There is a, let's say, scientific paper which is analyzing the opportunities how to go deeper with convolution. And the other paper, what I recommend you, the paper from Weiss and the co-authors, Survey of the Transfer Learning. It is a rather extensive, almost 40 pages discussion of the concept of transfer learning. And then the paper on deep learning of representations for unsupervised and transfer learning is, I believe, something which works worth attention. And Bashar paper on survey of evolving deep learning neural network architecture is paper which might be useful for many of you. And the last paper is on the topic of the layer-wise relevance propagation and overview of the layer-wise teaching in deep learning method. So this was the next module, next block. I stop here. I don't know if you have, please, any comments, questions related to what I mentioned.
Any question anybody has? Anyone having any question?
If not, that let's continue with screen sharing, and I hope you can see my desktop. Can you?
Yes, we can.
Thank you so much. So then, keeping the end of the second presentation in mind, in the break, I removed a couple of slides from this content in this fourth block, and I hope that what I mentioned about convolutional learning, together with the explanation what you received from the video and what you can have from other sources, for instance, the MATLAB environment, will be enough for you to understand a little bit deeper. So the convolutional neural network consists of many layers, but follows some semblance of pattern of convolution, especially with regards to the value layer, which makes which is applied multiple times and makes pooling multiple times. Convolution is a mathematical way of combining two signals from a third signal. And convolution means convolving the input image from a series of filters that highlights features without losing information. Convolutional neural networks are most appropriate for image classification since they are good at local spatial pattern matching. Convolutional neural networks usually outperform other methods for image feature extraction and, in certain cases, even human. Common configurations of convolutional neural networks are, for instance, the series networks, LXNet, parallel directed acyclic graph, DAG network, and, for instance, the Google map. Implementation of the convolution needs to define specific connectivity between the neurons, and this connectivity tries to mimic the functionality of the primary visual cortex in the brain. A neuron in a specific layer is connected only to a set of spatially adjacent neurons in the previous layer. Neurons in the convolutional layer should wake up the corresponding input neurons with shared weight values. The output of the convolutional layer is called the feature map. This arrangement provides an output in which a single feature detected in the input appears. The convolutional layer is usually followed by a pooling layer. The pooling layer takes a feature map and tries to summarize it in the layer in a larger region. So this is how we can understand very simply the principle of convolution. So actually here we have a systematic scanning procedure in the background, and from the input image, the certain regions are addressed at a time, the features are extracted from that, and then through the multiple convolutional layers, they are feeding the pooling layer, and then after that, again, convolution is applied, and then the extracted partial feature or features go to the fully connected layers, which are subsequently generate the output on the last layer. The neural individual stimuli, however, is only a stimuli to a restricted region of the visual field known as receptive field. So this receptive fields concept is applied in the convolutional neural network for identifying the focus of attention time to time. The receptive fields of different neurons partially overlap so as they cover the entire visual field. The convolutional layering is very well explained in a particular paper which I put here as a kind of reference, and the role of the pooling layers, the convolutional layers with regard to single feature marks, as well as the shared weights are very well explained and exemplified in this particular paper. The process of feature mapping is actually taking place in 4 steps. The first one is teaching with example. The second is sorting and working up the identified features. Then the extracted feature details are recomposed. And then there is a kind of coded structure produced, which is actually the kind of solution based on the teaching examples. Convolutional learning works in 2 phases, and this has been already shown by the image in the video, that the first part is feature learning and the second part is the classification. There are strong classificators in the field of traditional conventional machine learning, so this is what was recommended earlier for you to consider. So if the feature learning and classification stages can be separated, then by using dedicated classifiers, you can improve the working of a convolutional network. The feature detection layers obviously may be varying in numbers, and they have different functions: convolution, pooling, linear rectification, operation on the data. So we can say that each layer is designed to learn to detect different features. Convolution puts the input images through a set of convolution features, each of which activates certain features from the images. Pooling simplifies the output by reducing the number of parameters that the network needs to learn about. So it is performing a non-linear downsampling. And then the rectified linear units, the ReLU, allows for faster and more effective training by mapping negative values to 0 and maintaining the positive values. These operations are repeated over hundreds of layers, as was mentioned. The object classifier classification layer is engaged with the feature detection, and actually it has a innate classification architecture. Classification starts with flattening the outcome of the feature recognition layer. The next to last layer is a fully connected layer, typically in convolutional layer, and it outputs a vector of k dimension. The k is the number of classes that the network is able to predict. The vector contains the probabilities for each class of any image being classified. The last layer of every convolutional neural network architecture uses basically the softmax function. You can find it also in the, and you can find also the usage and the interpretation in the MATLAB environment. This is used, the softmax function is used to provide the classification output. There is no exact formula for selecting layers. The best is to try a few and see how well they work, or to use a pre-trained network. So the steps of training are as follows. First of all, you need to set up an input-output relational database matrix. Then, sorry, I heard something. I don't know. Was it a question to me? Okay, if not, then I continue. So sorry, again, I heard something.
No, it's okay. I just wanted to continue. Please continue.
Sorry, I didn't know it was a question because I was busy with talking. So the first step of training is set up the input-output relational data matrices. The second, initialize the network parameters randomly, then feed data through the network forward, of course it happens with forward propagation. Then adjust the weights and activation functions based on an error, present all training examples individually, readjust the weights and activation functions based on the experienced error, monitor the error in the output, and adjust the activation function, use sigmoid, tangent, hyperboid, rectified linear unit type of function, leak relu, max out relu type of activation function, and find the stationary point. This concludes my brief overview of the convolutional learning principle. And let me suggest a couple of literature items which I believe can be useful for you. First of all, an early paper from Butler towards a connectionist cognitive architecture, which gives a very good insight into what we can expect from the connectionist and convolutionist working. Then the next paper is providing knowledge about understanding of the convolutional neural networks, how they work, what types are out there, and what can you do with it. It is a relatively short paper, so easy to study, so I believe before the exam you can have a look into. Another paper is a recent one, and it summarizes the recent advances in convolutional neural networks. The fourth paper, what I suggest to is a very recent one. It is a survey of convolutional neural networks, and it analyzes how they develop, what applications do they have, and what are the promises for the future. Then the last one is about the evaluation of convolutional neural networks for visual recognition. I mentioned that for a long time, convolutional neural networks are typically focused on visual image processing, and this particular paper evaluates the stages some 20 years ago about what was there, and based on then you can conclude what can be expected currently from the convolutional neural network. So this is the end of my second lecture, leaving out a good couple of slides. I could manage the time keeping, and what you have heard from me in this second block, in the second lecture, was that the first block looked into the fundamentals of deep learning, and it discussed many technical issues which I believe important to be taken into consideration by CPS developers when they make a choice or when they want to select the best applicable deep learning or convolutional learning method for their purposes. The second block dealt with the but really just conventionally with the respective time with the principles of convolutional learning. So thank you for your attention for today. Please stay tuned for the next lecture and for the afternoon when you go on with the practicum. I don't know if Professor Tandon announced or not that on Friday during the practicum time you are supposed to complete a 1 hour and test and examination. The style of it will be very much resembling to the entry test style, but the questions are completely different, obviously. But all the questions can be answered, definitely, I know it, based on what.
Okay, Vivek, do you have any question?
No, sir. No, sir.
I think all of you are clear with what Professor Imre has announced just now. The same is what I announced yesterday also, that on Friday, last class, 4:30 to 5:30 p.m. Indian Standard Time, we'll have a small quiz on the what you have learned, what you have gained from this particular GIAN course. And the style will be same as we have asked you at the entry level, a pre-course quiz. Like what is like what are the different factors, what you have learned. It will be similar to the content which has been delivered by Professor Imre on in these lectures. The only thing is that you have to be honest and you have to answer. That's a mandatory requirement. So I expect all of you to be present. Don't skip. If you skip, probably it will be difficult for us to award you certificates or any other thing. It's not going to be tough, and it's not that you will be awarded any grades out of it. So more important is an honest attempt from all of you to answer so that we know what you have gained out of it. Any comments? Okay, then let's have a
The only, excuse me, Pune, just because I always have the strong intention to help the students to achieve their best, the only thing what I would like to mention that don't start going through the presentation from the first to the end. Please look into the content of the blocks. Every block had a particular topic. Please go through the topics of the block and then ask yourself the question, do I know what I can answer to it if I am asked? If you come across with a particular block for which you are not sure if you can have answers directly, then please look into that particular presentation. Start this way, bring up yourself to an equal level of understanding and first focus on the weak spots. Then when you brought up yourself to a kind of homogenized knowledge level, then you can look into the presentation materials or even look into the suggested literature if you feel yourself tempted. Thank you so much, Pune. I hope that it was useful for the students to hear about the systematic approach, which is typically applied when we have online courses and the whole material is chunked into units, like here. Thank you so much.
Perfect. So, if no question, no comments, can we have a photograph session? Any photographs? All of you, please switch on your cameras. All of you, please switch on your cameras. Mandoi, Chinmay, Ruchika, Keshav. Chinmay, Ruchika. Am I audible to you people? Can you just switch on your cameras? Chinmay and Ruchika. Okay, then if you are not listening. Okay, thank you. And as you
Thank
are
you
aware
so
now,
much. And tomorrow we will talk about agent technologies and also the issue of model-based and component-based creation of cyber-physical systems. So hope the topic will be interesting for you. Please join.
thank you, Professor Imre.
Thank you, sir.
Thank you. And we'll start the next session at 4:30 p.m. IST. So you have approximately 20 minutes break time. So we are able to compensate what we couldn't do in between the first and second session. Since we couldn't give you break in between the first and second, no exception. So we'll start sharp at 4:30 p.m. Okay, thank you.
Thank you so much for the participation. See you tomorrow morning. Bye-bye for now. Bye-bye.
Are you ready? Welcome back. We're going to start the next session in just a few seconds later. Am I audible to all of you?
Yes, sir. Audible, sir.
Yes, sir.
Okay. Chinmay, you don't have a camera?
Yes, good afternoon, sir.
Good
Sir,
afternoon.
I have to start the camera.
No. I'm asking about Chinmay actually.
Okay.
Chinmay, am I audible to you?
Yes, sir, you're audible.
So you adjust your camera. You didn't open your camera when we took the photograph at 4:15. So you have to open
Sir,
after you finish this thing.
Sir, actually, my internet connection was unstable, so I might have left and rejoined. That might have happened.
You were there, but your camera was not on. Anyway, now when we finish this class at 5:30, please switch on your camera so that your presence can be recorded.
Okay, sir. Sorry, sir.
Okay, so let's start with today's hand-on session. And as Professor Imre Howard has taught about CNN basically in today's lectures, today's both the block of lectures. So in today's hand-on session also, we'll try to learn the practical implementation and practical application of convolution neural network, CNN. And we'll just try to develop a small CNN model for some application, and not very interesting, but very apt application for today is the COVID detection. And everybody is one way or the other connected with the COVID actually. So in today's lab session, we develop a small convolution neural network, CNN, for COVID detection. And the data set which we'll be using will be for consist of the images consisting of just X-ray, which we have captured from different X-ray machines. And these images, based upon the CNN model, will be classifying into three categories: the normal images, the images with pneumonia, and images with COVID. And our objective is to develop a CNN model for COVID detection with the help of chest X-ray images. Once we develop this model, and once the model is trained, then this trained model can be tested on unknown images also, which is our major task. So when we get any, like for example, any person like you or me, we have a chest image and we pass to our CNN model. The model should be able to tell us whether you or I are normal, having pneumonia, or having COVID. So COVID is no more a dreadful word. That's why we took this liberty of taking up this particular case. And because the time is limited, so we'll try to teach you, and sometimes we have to go faster for this particular model. But the idea is the same way you can develop a CNN model for any cyber physical application also. Although we are talking about societal cyber physical system. So COVID detection is also a societal application, a healthcare automation service, where just by your chest X-ray images and without the help of doctor, we can have a model which can tell you, yes, whether you need medication for COVID, whether you want to be hospitalized, or whether you need to be hospitalized, or whether it's okay with you. So this is the task for today. And in this journey, I'm happy to share that we have another research scholar, Purnima Singh Thakur. Purnima is a PhD scholar in the CS department under the guidance of Professor Pranita Ojha. And she has been working extensively in the area of CNN and with deep learning, AI, ML. I couldn't find any person better than her to take us along in this journey because of her great exposure to these types of models and hands-on experience actually. So I welcome Purnima, and I thank Purnima for taking this hands-on session so that she can train you how to work on this. And any question, I am here. She's here to help you. But the idea, as we did yesterday also, that if you can start using your machines or your laptops and start developing model, that will be good. But in any case, if you're not able to do it also, no issues. Please remember that we have these recordings available on YouTube also, and we'll share shortly the live sessions also. You can just follow up the instructions and develop your own models. Okay. Anything else, Purnima, you want to convey to them? Otherwise, the floor is all yours.
Thank you very much, sir. So, sir, I'll share the data set with all. So, if anyone wants to work parallelly, they can do the same.
Okay.
So, participants, very good afternoon. I'm going to share the data in the chat box. You can download. It is a zip file. Now you can download the data set from the chat box. Very small.
Ma'am, the slide is not visible.
Not shared. So now I have shared. You can download the data set. It is available in the chat box. I have shared. That is COVID_split.zip. It is a zip file which you can directly upload on your Google Drive. And we are going to do this hands-on session through Google Collaboratory, as explained by Samir sir. We can use the service of Google to deploy any type of deep learning model or any Python programming based model you can do on Google Collaboratory. So as you can see, here I am in my drive. Either you can create a Google Collaboratory notebook from here in this mode. Here it is Google Collaboratory. If it is not there in your drive, you can add a new application. From more, you can connect to more app, and then you can select Google Collaboratory and install it in your drive. Then you can create a new notebook. So in the today's session, we are going to develop a small CNN model. So why CNN? Because when you are working with large size data, then basic neural network or artificial neural network will not be a perfect solution due to the large size of the model as well as the large number of trainable parameters. So for images, or you can say a large size data, we use CNNs. CNNs have the concept of parameter sharing. Other than that, they have a small detector that we call filter or kernel that convolve over the entire image or any other type of data and get the features of that particular image or data set. So you can see in my case, there is a notebook created. From here, I can change the name. Other than this, whenever you are working with on a large size data, you have to change your processing or processing unit from basic CPU to GPU. That we can do from this runtime option. From runtime, you can change the runtime from hardware accelerator from none to GPU. After this, we have to access the dataset that is there in my drive, this COVID_split.zip. So first of all, we have to connect this collaboratory with our Google Drive. For that, we have this files menu on the left side. You can see in the left panel, files menu is there. I'll click on this files menu, and then this GPU will connect to the cloud of Google, and some memory, RAM and GPU memory will allot to this particular notebook. So you can see we have 12.68 GB of RAM and 78 GB of storage available. But we are not going to use that particular storage. We will use the drive storage, because when you use the collaboratory storage, your data will be truncated after 12 hours. So to store it for a large time, we will use, or permanently, we will use the Google Drive. From here, you can see mount drive option is there. So I'll click on this mount drive option and then connect to Google Drive. It will ask you for the permission. If you are working for the first time, in my case, I'm using the same system for collaboratory from a large time, so it is not asking for authentication. So this is my drive. I have placed the data in this GIAN CPS 2022. So I'll copy the path of this folder. Then I'll change the current working directory from this collab workplace to Google Drive. So this Jupyter notebook provides you operating system as Ubuntu. So all the Ubuntu commands or Linux command will work here. You can see there is a zip file, COVID_split.zip. We have to unzip it. So unzip space COVID_split.zip. And then I will comment it. It is a small data set. If you want to work with a large data set, you can do that. But as we have to train the model with and complete the model within 1 hour, so we have taken only 150 images, and the images are splitted into 3 portions. One is for training, one is for validation, and one is for testing. On the training images, that consist of 80% of the 150 images. We will train the model, and then after each iteration or each epoch, we will test the model performance on validation data. And at the end, after completing the whole epochs, at the end, we will test the trained model on the test data set. After unzipping, one more folder will be there. You can see this is the folder COVID_split. So let me show you what is there in the splitted unzipped folder. So it has test, train, and well 3 folders are there. And when you check inside the test, there will be 3 folders, one with COVID, one with normal, and one with viral pneumonia images. Similarly, in the train, 3 folders are there. And in the same way, validation folder have these 3 subfolders there. So in COVID folder, all the images having COVID X-rays are there. In the normal folder, normal X-rays are there. And in this viral pneumonia folder, X-ray of the patient which has pneumonia are present. Our next task is to work with CNN model to develop a classifier which can separate or identify COVID, normal, and pneumonia using this CNN. So there are various ways to read the data, but in case of CNN, a library is there named as image data generator, which helps us to read the data. And using that particular library, we can perform various pre-processing tasks as well. So we are going to use the same. So let me import the package from Tensorflow.keras. So today's CNN practice will be on Tensorflow's keras package. Other than this, you have option to work with PyTorch as well. Tensorflow.keras.preprocessing.image. This is for images. We are going to import image data generator. Using this image data generator, we can define various pre-processing steps which we can perform on images like image resizing, rescaling, normalization, data augmentation. Various options are there which you can pass like a parameter inside this image data generator. We are going to perform only normalization of the images. In the normalization phase, all the pixel values of the images are divided by 255. That will so that the image pixels will range between 0 to 1 instead of 0 to 255. So this is the process which you have to follow whenever you are developing any type of neural network. Your data should be normalized. So then I'm creating one object for this particular class, that is data preprocessor. I'm creating. And later on, we will use this preprocessor to read the data from the folders. So our data is there in the folders or directories. So one function is there to read the data, that is flow from directory. We are going to use this. It takes multiple parameters as input. The very first parameter, as you can see, it is suggesting what are the parameters flow from directory takes. The first parameter is the directory or the path of the folder, which consists of your any type, training data or validation data or test data. So our data is there. You can see it is there in COVID_split/train that I'll give in the codes. Then when you then the next step is to resize all the images in a fixed size, whether you want the image should be 100 × 100, 200, 256, whatever you want. So I'm resizing all the images into 64 × 64. So whatever your image size is, your when in this step, all the images will be resized as 64 × 64. So our convolution neural network will take the input of size 64 × 64. Then the class mode. This is another parameter you have to pass in flow from directory function. If you are working with single class classification, then or binary class classification, then you have to use binary here. But we have 3 classes, so we will use categorical as class mode. Next is batch size. So what is batch size here? Batch size defines the number of images or number of data points you want to process in one step. So it depends on your memory availability of the memory. If you have large memory, you can set it 64, 128 as well. But if you have small memory, you can set it 4, 8, 16. Generally, it is power of 2 generally, but you can set anything. Then there are some more parameters you can take. I'm not taking more parameters as input. All the output of this particular file or this particular function will be stored in a temporary variable that we are taking as train data. That is our training data. Similarly, I'm going to create validation data. All other steps will be same. Only the difference is I'm changing the path of train to well. Similarly, we'll create the reading step for test data. So here we have to add one more parameter that you can add in the validation as well. That is shuffle. So by default, this shuffle parameter, when you work with shuffle, it is true. That means your data will be shuffled after each epoch. So for test, I'm making it as false so that it will not shuffle your data. What is directory is missing. Let me check. Okay, I have to pass this particular. This is the object we will use to read the data. So you can see in the training folder or train folder, we have 120 images present in 3 classes. Similarly, in the validation folder, we have 15 images in 3 classes. That means 5 images from each class. Similarly here, 5 images in each class for test data. So our data is divided like 80% we are using for training, then 10% for validation and 10% for testing. This is the step of data reading and data pre-processing. So there are multiple ways you can read and pre-process your data. This is one of the pre-processing steps we follow. Next is creating your CNN model. So that also we have multiple types of codes to write the model creation or model development. We are going to follow one of the way. If you want to get multiple ways of creating the model, you can go through the website keras.io. It has all the tutorials. Various options are available. You can go through various options of developing your codes. So some examples are there. You can see image classification and multiple options are there. You can follow these steps to create your model. So let's create the CNN model from tensorflow.keras. We are going to import models and some layers. We are going to create a CNN model. There are two ways to create any type of models in Keras or TensorFlow. One is sequential way and one is functional API way. In sequential way, your data will be, you can give only one input as in the model, and your layers will be added using the add function in the sequential model. In functional API way, you can create the model with multiple input as well as multiple outputs. So from these models, we are going to create sequential. This is the way you can create the model. And then you can add the layers in the model. So the very first layer we will add is input layer, layers.input. Using this layers, we are going to access the input layer. So as you can see in the target, we have assigned the input size as 64 cross 64. So here also, the input shape will be 64 cross 64 cross 3. If you are working with color images, then it will be 3. If you are working with grayscale images, then it will be 1. After that, we will add some more layers of CNN. In CNN, the basic layers we will use are convolution layers and pooling layers. Other than that, we generally use normalization layer or batch normalization layer. And at the end, we use flatten layer or global average pooling layer to convert your data into one-dimensional vector. And at the end, we use a dense layer to classify the image. So let us add some convolution layer over here. From layers, we are going to use convolution layer. So that is conv2d, layers.conv2d. So this convolution layer takes multiple parameters. One of the parameter is the number of filters. So this is also generally power of 2, and there are two ways to develop CNN or decide the number of kernels in any convolution layer. Either you can increase the number of kernels layer by layer, or you can decrease. So it depends on your application that which type of layers you are going to use. So here we are going to use 8 filters, as our data set is very small. So we are going to develop a small CNN model with small number of kernels. Next is kernel size. This is of size 1 cross 1, 3 cross 3, 5 cross 5, whatever you want to convolve over the image. So we are going to use a 3 cross 3 kernel. In most of the application, you will find that the kernel size is 3 cross 3. Then activation. So this activation function is used just after the convolution layer or in after performing the convolution operation to activate or to boost up your resulting vector or output. So here we are going to use ReLU as an activation function. So this ReLU works as that whatever your negative, the output of your convolution layer is, if it is negative, then your activation will convert that output as 0, and the positive output will be same. So to avoid the negative outcome, we use ReLU. So as per the literature, in hidden layers or the in the hidden layers of your neural network, we use ReLU as an activation function. So this is the first convolution layer we have used. Next is, let us add another convolution layer, layers.con2d with 16 filters or 16 kernels and kernel size as 3x3. Activation function we are going to use is ReLU. So let us just add one max pool layer over here. CNN model dot add layers dot max. And the pooling size is 2x2. We are going to use the pooling here as 2x2. Then the output of this max pooling layer, we are going to pass it to the output layer, that is a dense layer. Before passing it to output layer, we have to convert it into one-dimensional vector. That we can do either by global average pooling 2D or average pooling 2D, or we can also use the flattened layer. So flattened layer just reshape the output of your max pool 2D, whereas global average pooling or global max pooling layers average the pixel values by the depth of the feature map of the max pooling layer. CNN model dot add layers dot, we are going to use flatten layer. And then we are going to add the output layer, that is generally have densely connected layer or a dense layer. Here you have to pass the number of classes in the data. We have 3 classes, so we will have 3 neurons in the output layer. And here we have to change the activation function. The activation function here will be softmax. So let us test whether the code is correct or is there any error. Activity shape. There is one typo. Now the code is correct. You can see. Next is to check the summary of the model. What are the input shape or output shape of the model, the number of parameters present in the model for training. So that you can do using model name dot summary. So this is our model, which has first hidden layer as con2D, second con2D, third is max pooling 2D. Then we have used flatten and then dense. These are the output shape of each of the layers. So after first convolution layer, the output shape is 62 cross 62 cross 8. You can see our input is of 64, but the output is 62. So the formula is n minus f. That is your input size. That is 60. So n is the number of pixels or height or width of your image, that is 64, minus filter size. So filter size is 3. So 64 minus 3 plus 2 into padding. So we are not going to use padding. So that is not there. Upon stride. So stride is by default 1. That is the your filter width will move only once while convolving over the image. Plus 1. So it will be 62. So that's why our output shape is 62 cross 62. And this depth is 8. The reason is we have used 8 kernels or 8 filters in the first convolution layer. Similarly, this will be calculated in the same way, height or width of the image minus filter size or kernel size plus 2 into padding upon stride and then plus 1. So it will be 60 cross 60 and this 16 will be from here. In the same way, whatever will be the output of this max pooling, that will be reshaped or multiply with each other, 16 cross 30 cross 30, and this will give the output of the flattened layer. So this is very important part, this params, that is trainable parameters of your model. These are the parameters which will be learned while your training process, and depending on these parameters, your model performance will fluctuate. So you can see in the first layer, we have 224 parameters or 224 trainable parameters are there in the first hidden layer, first convolution layer. That will be calculated using this kernel. Your kernel size is 3 cross 3. It is applied on the depth of the image. So your kernel size will be 3 cross 3 cross 3. That is 27. And it is total number of kernels we have 8. So that will be 3 cross 3 cross 3 cross 8. That is the size of your kernel, number of elements in your kernel, plus number of biases. So number of biases are the total number of kernels, that is 8. So 8 will be added at the end. So the final parameters will be the kernel size, total size or total elements present in the kernel, plus the biases. So the kernels are the weight matrix or the weight we are going to learn while the training process. That is 3 cross 3 cross 3 size of single kernel, 3 cross 3 cross 3. Total number of kernels will size will be 3 cross 3 cross 3 cross 8 and plus 8, because we have 8 biases or 8 filters here. Similarly, in the second convolution layer, the trainable parameters will be calculated like 3 cross 3, but here the depth is 8. So the kernel size will be 3 cross 3 cross 8, single kernel of size 3 cross 3 cross 8, and total kernel size will be 3 cross 3 cross 8 cross 16 plus the biases. So 3 cross 3 cross 8 cross 16 plus 16 will be the trainable parameter here in the second convolution layer. In the max pooling layer, there is no kernel or no weights or training present, because it just reduce your image or input size or feature map size to whatever you will assign as pooling size. We have assigned the pool size as 2. So your size will be reduced to half. That is 30 cross 30. Here the filter size, the depth will be same 16. Then in the flattened layer, it will be multiplied 30 cross 30 cross 16. So again, there is no training involved while flattening layer. So it has 0 parameters. But in the output layer, these 14,400 neurons are connected to these 3 neurons. So that's why the number of trainable parameters here are very high. So 14,400 cross 3 will be the size of your weight matrix. And for each neuron in the output layer, one bias will be associated. So the total number of trainable parameter will be 14,400 cross or multiply 3 plus 3. So these are the parameters. Then the total trainable parameters are 44,595 in this particular model. When you increase the model size, the trainable parameter will increase. There are models which has parameters in millions or billions also. So it depends on your data. If you have large size data, definitely you have to increase the depth of the convolution neural network to learn the features of the data or images properly. After this, we have to train the model. So for training, before training, we have to set some hyperparameters like what will be the optimizer, what will be the loss function, what are the metrics we are going to use for to evaluate the performance. So that also you can use from the Keras API. From Tensorflow.keras, we have to import optimizers. There are multiple optimizers present like SGD, stochastic gradient descent, ADAM, AdaGrad, AdaDelta, RMS prop, NADAM. Multiple optimizers are there. You can test your application with all these optimizers. Whatever optimizer best suit in your data will be the will only depends on your data. We cannot say that SGD is best or ADAM is best. It depends on your data that which optimizer is working best. So let's define the optimizer as ADAM here. So we are going to use optimizers.ADAM. Similarly, you can use optimizers.SGD or optimizers.RMS prop NADAM to access the optimizers. Again, to read about various optimizers, you can go through the Keras.io website. There they have the implementation as well as the respective definition of the or the corresponding paper where the optimizer is introduced. You can read that for your reference. So here in this optimizer function, we have to pass some basic parameter. The very important parameter is learning rate. This learning rate defines that how your weight update process will be. Prashant sir, can you unmute? Prashant sir, mute yourself.
I'll do it. Don't worry. I'll just do it.
Thank you. So here the learning rate defines the phase in which your model or the weight update process will be performed. Initially, your weights are these parameters. Initially, your weights are assigned randomly. Then, while the training process, your weight update process is performed, where the weights are adjusted based on the learning after each epoch. So, the updation of the weights are dependent on this optimizer, and this optimizer depends on this learning rate. So, generally, the learning rate is in between 0.001 to 0.0001, or it again depends. Yeah, it is a hyperparameter, so you have to test with multiple learning rate to check which is working well. Here we are going to use 0.4 times 0, then 5 as a learning rate. Then the model which you have created, here you have to assign the optimizer, loss function, and performance metrics you are going to use. So for that, you have to pass the model to the compile function. So CNN_model.compile. The first parameter is optimizer that we have already created. This ADAM. Next is the loss function. So again, the loss function, there are multiple type of loss functions present. It depends on your application. We are currently working with an application of classification. That too, our data is in one hot vector. One hot vector means that your output class is a type of list or array where the size of the array is the total number of classes. For example, here we have 3 classes, so our array of size will be of 3, and whatever class is present, that will be 1, all other will be 0. So that is one hot vector. So that's why we are going to use categorical cross entropy loss here as loss function. If you are directly passing the class value as 0, 1, 2, 3, that whether it belongs to 0 class, 1 class, or 10th class, then you can use sparse categorical cross entropy loss, and so on and so forth. Multiple loss functions are there. You can use MSE, RMSE, even you can develop your own loss function. And then the last parameter we have to pass is matrix, performance matrix you want to use. Here also you can calculate true positive, true negative, false positive, accuracy, precision, recall. Multiple parameters are there. We are going to use accuracy as performance measure. So this is all to develop a model. Next is you have to train the model. So for training, we have fit function, CNN model dot fit. Here you have to pass your training data and the validation data. So training data will be helpful for training and weight updation. After that, weight updation using the optimizer. And then the validation data is to check the performance after each epoch. Here we call iteration as epoch, but there is a slight difference between iteration and epoch. So in fit, you have to first of all pass the data that is there in train underscore data variable. So this is our training data. Next is you have to tell the epochs. So let us train it for some 10 epochs. It again a hyperparameter. You have to test at which epoch your performance is degrading, then you can stop it, or you can also use the concept of early stopping. So your model will automatically stop when your learning will be done. Next is you have to pass the validation data. Here our data is there in val underscore data. In the output, we are going to store in a variable named as result. Let's check what is the performance the model is giving. So you can see this is the first epoch which has been executed in 13 seconds. Then the loss is 1.1213 for first epoch. The accuracy or training accuracy is 37.50. The validation loss is 1.08. Validation accuracy is 33.33%. In the second epoch, you can see there is a slight decrement in the training accuracy, but the validation accuracy is as it is. Validation loss is again decreased. Here also validation, the training loss decreased. After some epochs, the loss for training loss and validation loss is decreasing, whereas the accuracy is increasing. So you can train it for some more epochs, maybe 20, 30, 50, 100, depending on your data size. Currently, it is enough to train it for 10 epochs. Next is, generally, we check the epoch-wise performance using the graph, training graph and validation data graph that Samir sir has already explained, I think, in yesterday's session. Using matplotlib, you can plot the training graph, training and validation graph of your epoch-wise performance. So let us do that. It will hardly take maybe 2 to 5 minutes. Import matplotlib.pyplot splt Then the steps are the range of 10, 0 to 10. Then training accuracy we have in the output will be there in result variable. So result dot history, it is a list where from where we will access accuracy, only accuracy. Similarly, we will access validation accuracy. Then plt.plot steps, where we will pass the training accuracy. And validation accuracy. So this is the trend of your accuracy, training and validation accuracy. Similarly, you can check the trend of loss. So you can see the loss is decreasing. So we can train it for some more epochs. When you find that this graph is flattening, then you can stop the training. So let me show you that also. Now I am training it, the same model I am training for 30 epochs. It will hardly take a minute. And then we will see the trend. So these all are hyperparameters. We have to decide that we can do by checking these graphs and then the performance. Steps have to change here from 10 to 30. So you can see now there is a slight variation in the performance, and this graph is also going to flatten. So this is the way you can check whether your model is trained properly or not. So if you train for some 10 or 20 epochs, then you will find that this slope is flattened. Now let us check the performance on the test data set. As you can see, after 30th epoch, the training accuracy is 86.67%. Similarly, the validation accuracy is 86.67. Now let us check what is the performance on test data set. If it is nearby, then your model is perfect. If it is giving very less test accuracy, that means you have to fine tune your model again. So for check the performance on test data set, you have evaluate function with you, CNN model.evaluate I'm passing, that is giving loss as 65% and accuracy as 53%. That means we have to fine tune our model. You can increase or decrease the number of layers. You can use data augmentation techniques, or the number of epochs you can change. You can also change the learning rate. Then you can achieve much better performance. And if the data set will be, data size will be more, then there are chances that you will get nearby performance. Next is to check the performance on unknown data set. Either you can download one image from internet, like say, or what you can do, you can use any image from test data set to check the performance. There is some issue. We use it from the test data set. So in yesterday's session, you must be understood what is CV2 or OpenCV library we generally use for image data. So I'm going to use that library, CV2, import CV2. Then we are going to read cv2.imread any of the image. So let me use from test data. I'm using from test data that is unknown to your model because we have not trained the model using these images. After that, we can use plt.imshow to plot the image. So this is the image. Next is to identify or predict the class of the image using this this particular image. We have to first of all check what is the image shape or image size. That is image.shape, that it is of size 299 cross 299 cross 3. We have to reshape or resize it to 64 cross 64. That will do using cv2.resize our input image and then the shape in which we want to resize. Now when you check the shape, it will give you 64 cross 64 cross 3. So whenever you are working with unknown image or unknown data, first of all, you have to perform the same pre-processing steps you have done for your original data while training. Next is our model, that is CNN model dot predict. Here also what you have to do, you can see the image shape is 64 cross 64 cross 3, but your CNN model takes the image in the form of batches. Either you can reshape it into 1 cross 64 cross 64, that is upshape 4. When you, so let me tell you what I'm explaining. When I'll pass the image directly, it will give me error. You can see that the expected shape should be like this, none cross 64 cross 64, but I'm passing something like this. Okay, so what I have to do, I have to reshape it. This image dot reshape. The first shape in place of none I am passing as 1. Then second is whatever of the shape 0, that is 64, again shape 1, that is 6. This is shape 0, shape 1, and this is 3. 3 is shape 2 dot shape 2. Now when I'll check the shape, it will give me 1 cross 64 cross 60. There is typo. It will give me 1 cross 64 cross 64. Okay. 64 cross 3. This is the shape. Now it will not give me any error. In place of that, it will give us the probability of all 3 classes. So when you print it, you will see that it is predicting class 1. So this is class 0, then this is class 1, this is class 2. So for that we have to first check what represent this 1, for which indices 0 is representing which class. So for that we have to use any of the data. So let us use test data dot class indices. So the 0th class represent COVID. If 1 will be here, then images from normal, and if 2, this 1 is available and these two are zeros, then you have viral pneumonia class. So this is the way you can predict the COVID in unknown images as well. So is there any doubt anyone have? Any doubt till now?
No, ma'am. No, ma'am.
Okay,
No, ma'am.
thank you. Sir, I have completed the part.
Okay. So all done?
Yes, sir.
Okay. Thank you. That's good. Any question from anyone? Anybody has any question? Have you practiced or you've just understood what Purnima was telling you? If you have practiced parallelly, good. Otherwise, please have a look at the channel and try to practice it on your own. You have shared some file?
Yes, sir. I have shared this Python notebook for practice.
Okay, good. So finally, no question. Then can I request Purnima to stop sharing the screen and all of you just open your camera so that we can take a quick attendance report. Please switch on your cameras, the remaining people also. Purnima, you can also switch on the camera if
Yes.
possible. Anand, Jefferson, ST, Rahul. Anand, are you able to listen to me? You unmuted, but just one. Okay. Please keep on your cameras. Srinivas. Okay. So smile, please. Ishan, take off your hand. Thank you. I think that's all for the day. If anybody has any comment, you can share. Otherwise, we can stop sharing the screen. Any question from anyone? Okay, otherwise, we'll meet tomorrow, 2 p.m. sharp, with the next lecture of Professor Indra Howard. Thank you and have a nice evening. Bye.
Thank you, sir.
I'm just